Welcome back, Pre-Calc. Hope you all are well. Our objective today is going to be to continue to analyze rational equations or rational functions. Remember, rational, fractional. So these are functions that have like one polynomial over another polynomial, look like fractions. So we're going to continue to analyze these today. If your teacher gave you a list of notes, go ahead and take those out. If not, they should be on Canvas, and if you have the ability to print those out beforehand, I would do that. Otherwise, you just need to pause each screen and write the guided notes along with me. So force pause on your screen, go ahead and check the checklist, and then grab those guided notes if you have them. All right, and force pause on your screen, can you go ahead and copy f of x in your notes for me? All right, so I just want to analyze this graphically, and then we'll go ahead and go point by point for each of our guided notes. But I first want you to look at your numerator and denominator. I have them in factored form for you already. And take a look at this factor of x minus 2. Notice that those cancel, or they remove, right? So what's going to happen is that even though it looks from Desmos, it looks like 2 is part of your domain. It actually is not, because if I set my denominator equal to 0, I have problems when x is 2 and negative 3, because both those x values make the denominator 0. Okay, so at negative 3, I can clearly see, well, that's a vertical asymptote, right? And that's because that's an x value that makes the denominator 0 that does not cancel out. Remember, that's a non-removable discontinuity. I cannot remove that factor of x plus 3. But what about this factor of x minus 2? In other words, if I go close to x equals 2. Well, let's see here if I can get close and show you that right at 2, actually there's what we call a hole. Did you see that? So at 2, if I can get it, it's the y value is undefined, right? Because I'd have a 0 in the denominator. But again, that's a hole and not an asymptote. It is a removable discontinuity as opposed to this asymptote, which is a non-removable discontinuity. Okay? All right. I would also like for you to notice that you've got an x-intercept at negative 4, right? That's what makes the numerator 0 after you cancel. You've got a y-intercept here at 1.3 repeating, also known as 4/3, right? Because that's what you would get when you plug in 0 for x after canceling. And then you have a horizontal asymptote at y equals 1, because if we do Bobo-Botten eats DC, it would be our eats DC scenario, and so leading coefficient of 1 divided by 1 is 1. All right, so let's go ahead and fill these notes out together. Again, if you don't have them printed out in front of you, go ahead and pause the screen and write down these steps, and we'll fill in the blanks together. But if you have them, let's go ahead and get started. So holes, that's the first thing we're going to do. Remember from our example that we first want to factor the numerator and denominator, and we want to see if any of the factors cancel. So canceled factors become undefined points. Those are removable discontinuities, right? I can remove those factors, and that's what we call a hole, right? That's a removable discontinuity. I can move or add just one point and make the function nice and continuous. So that's step 1, is find your holes. All right, step 2, we're going to find vertical asymptotes. So after you've canceled any factors, what do we set equal to 0 and solve for x to get our vertical asymptote? That is going to be the denominator. But remember, this is after you've canceled. Can you go ahead and highlight or underline that phrase for me? Okay, so vertical asymptotes and holes, remember, those are your discontinuities. So that's all about looking at the denominator, okay, because those are gaps in your domain. So you look and see where the denominator is 0. If if it's a factor that cancels, that's a hole. If the factor does not cancel, does not remove, then that is a vertical asymptote. All right, horizontal asymptotes and slant asymptotes. So for horizontal, remember this is our mnemonic Bobo-Botten eats DC. So bigger on bottom, y equals 0. So that would be this one, right? Eats DC is exponents are the same, divide coefficient. So that's your kind of middle bullet point here. So I'm going to put that's y equals a over b, where a is your leading coefficient of your numerator. and b is your leading coefficient of your denominator. Okay, and then if your power on top is greater, that's bigger on top, then no horizontal asymptote, or none. Instead, you might have a slant asymptote. So let's take a look at what slant asymptotes look like. So I first want to show you what do I mean by slant asymptote graphically. So you can tell here, hopefully, that there's this line, but it's not horizontal and it's not vertical. It's a slanted line that my function approaches as x approaches negative infinity and positive infinity. I still have this vertical asymptote. Take a look at my denominator. Where? At x equals 1, right? I'm talking about the slant asymptote, okay? So our question is, how are we going to figure that out? Well, take a look at my function. Take a look at line 1 here. Your numerator degree is how much larger than the degree of the denominator? It's just larger by 1, right? The degree of the numerator is 2, denominator degree is 1. So let's fill in our notes for that slant asymptote. So a slant asymptote is y equals, and I'm just going to put mx plus b. Okay, it's a line with slope other than 0 or undefined, right? And this occurs when the degree of the numerator is, how much more did we say? 1 more than the degree of the denominator. And here's how we're going to find it. So we're going to divide the rational expression using polynomial division or synthetic division if we can. And then we're going to end up ignoring the remainder. And I'll show you why, but it's going to disappear as x approaches infinity. Okay? So here's what I'm going to do. Can you, force pause on the screen, can you copy the same f of x that we had in Desmos just a while ago? All right, so we're going to do what the directions tell us to do here, and it says divide the rational expression, right, and then ignore the remainder. So let's divide. I'm going to put a 1 here, and then my coefficients 1, 2, negative 1. Bring down the 1, and then we're going to multiply, add, right? And so what I get is, put it over here, I get 1x plus 3 with a remainder of 2. So 2 over x minus 1, my original divisor. Well, think about this. Remember we talked about this as the denominator gets bigger and bigger and bigger and bigger as x approaches infinity or negative infinity. As this just grows, the absolute value of it grows, then that whole fraction is going to go away. It's going to approach 0. So that's why I can ignore my remainder. And my slant asymptote is this. It's going to be y equals x plus 3 in this case. Okay, my mx plus b. Let's take a look and see if it matches our graph. All right, so here's that graph we were looking at earlier. We got y equals x plus 3, and look at that beautiful slant asymptote, right? So there I can see that that is exactly what we are approaching as x approaches positive infinity, so to the far right, and negative infinity to the far left. All right, for x-intercepts, remember 0 over anything is 0, so we're going to set the numerator, oh dear, set the numerator equal to 0 and solve for x. Now, there's a little caveat here. This is after you have factor canceled, okay? So we're assuming you've already done that. Okay, so make sure that you factor first, and then once you're to the point of canceling, that's when you can go ahead, if anything did cancel, and go ahead and set the numerator equal to 0. Okay, y-intercepts, that is when x is 0, right? So we're going to plug in x equals 0, or 0 for x, and maybe not solve for, but simplify for y. All right, so very soon we're going to ask you to plot all these things and label all your asymptotes and intercepts and do these by hand. Right now, still, we're just going to go piece by piece. So can you find the x-intercepts here, vertical asymptotes for this one? And then the last thing we want to look at is domain and range, okay? So for range, you are welcome to go ahead and graph and take a look at the y values that are covered. For domain, there are two things you really need to watch out for if you want to do it algebraically, which I recommend because you may have a hole that you're not going to be able to see in your graph. So be sure to exclude x values that make the denominator 0 This is pre-factor cancel. So as soon as you factor, see, okay, is there anything that's going to make the denominator 0? Don't cancel out your domain. Okay, check your domain first. Or would cause negative values inside a square root. Right, those are the two things we need to watch out for. All right, you all, that is what I have for you today. I will see you next time.